And we'll be talking about using normalized differential vegetation indexes. A little bit of initial information. It's as we talked in the first session, this is based on electromagnetic radiation, which is a form of energy that travels in waves, and that includes almost everything that we experience, from radio waves, which are very long waves with low energy, to gamma rays, very intense, a very short wavelength. Somewhere in the middle, we have a big range of possibilities. There's a narrow range there that's a visible region, which is the things that we see. And we'll see what we use in agriculture. And the spectrum is what we call the range of all possible frequencies of this radiation. This is used in agriculture because there are reflectance properties of leaves and soils. Green plant leaves, they have low reflectance. That means that they absorb most of the waves that come in the visible regions. Why? Simply because it's absorbed by the plant pigments. And also the reflectance is high in near-infrared regions, and micrometers between 900 to 1300 micrometers. And this is, I'm not going to go into the detailed explanation because I don't understand it myself. That's for researchers, but it's related with the behavior of pigments and cell wall interfaces, why they reflect much more waves in those ranges. Whereas soils, they have reflectance, which increases through this visible and near infrared regions. So we can distinguish between them very, very easily when we have the information about an image about the reflectance. And inside soils, you can also have brighter, high reflectances in dry, smooth surface, and in wet soils you have, and with also organic matter, you'll have more absorption of the light. So, so that's what the basic property of leaves and soils, and you can apply this to every material on the ground. So that's why it's used all the way from forestry to geology in different applications. Now, but reality can be more complex because you have changes of proportion of soil and vegetation depending on the time of the crop season, and the arrangement of plant component varies. So there's a solution for that, which is vegetation indices, which basically combine these ranges, and they are a simple method for extracting the green plant quantity signal from this complex canopy spectrum, where you have the mixed signal between the soils and the plants, and that explains the basic difference between soils and plants, how they react. And basically, normalized or NDVI performs very well for tracking green biomass or leaf area index, which is the percentage of leaf against total area through the season, or detecting uneven patterns of growth. Many times, and I do this error myself, they're synonymous with plant health and vigor. In truth, this can be misleading because this we're talking about ranges and combination of ranges, and this lacks diagnostic capability, and really you need to use a narrower band indices are required. This is an example, chlorophyll ratio index. We'll be using a little bit of that in the last session when we work on chlorophyll detection, yield mapping in wheat. And so really it's a very practical way of monitoring green biomass and see where there are uneven patterns of growth. But to detect, for instance, fungus or water stress, maybe you need a more specialized approach or more narrow band detection. So basically, this is what we're combining. We're combining bands in the near infrared and red region, going back to that. So we're taking the values from different areas and combining them with this formula, which can compare the reflectance values of these two regions, and they help identify areas of varying levels of biomass. Basically, so when you have plants, growing plants with a lot of biomass, you have a lot of absorption, so the visible range will be absorbed, near infrared will be reflected, and you have a different situation when this is drying and there's not as much biomass. So that's what we have between 0 and 1. Those are the maps that will we interpret in your fields. And what you're going to be with a remote sensing system, it's basically you have a multispectral sensors that can be mounted on a satellite, on a plane, on a manned aerial vehicle, or a portable field device, like some of the commercial options that you have available, N sensors, nitrogen sensors, or SPAD meters, or, well, SPAD meters is another method, but you basically have sensors that can capture this reflectance. And what they capture are ranges of wavelengths in different bands. And for instance, we'll be using this imagery, Landsat, and a sensor called Thematic Mapper. That's on the Landsat satellite, which is a freely available resource from the U.S. government, which maps the world and in different bands and allows to derive useful information. And so this is just to give a rough idea. When you download imagery from the USGS, for this sensor, you'll be downloading 7 bands with different ranges of reflectance, different resolutions. And what you will be doing, what we try to do is assist the consultants in processing this quickly. It's combining bands to obtain the NDVI. So it's no more and no less than that. When you use other satellites, you will have some slight differences, or a plane. So you also have a multispectral camera that will help you define this. Okay, so I'll go to the practical data in a minute. Okay, so what are we going to use this for? Some things we will see. It's determine the issues affecting the health of the plant prior to harvest. Some things may be irreversible, but changes can be made for the next one, or some things can be corrected. And we also find a high correlation to a yield map, so it's really a good surrogate for yield mapping, and you just have to know when to take the imagery. At higher resolution, you can see other things such as nutrient deficiencies. You can use this for targeting tissue tests, soil samples, equipment problems such as compaction, depth control, locate tiles, or insects and disease pressure. What we will be seeing is more and more use as we know more of the applications, what we're trying to do in this course, and bring in specialists, and also having more affordable, higher resolution options with more applications. So really it's all technology that's converging to more effective use. This is what you will see when you process imagery, 30-meter resolution, which is Landsat imagery that we'll be processing for your fields. Or, for instance, at 5-meter resolution on the left, it's a rapid eye image, or at 1-meter resolution could be an aerial or unmanned aerial vehicle. So the range of applications will change according to the image that you're bringing.